Moving up next, we have a talk from Abhijeet Dhoke from Tata Consultancy Services, and he'd be speaking about leveraging behavior trees for task execution.
Hello everyone, I am Abhijeet Dhoke.
And I am Saleh Adityan.
So we are both research engineer in TCS Research. So in this talk, we'll be sharing the lessons which we have learned while designing task execution for the autonomous mobile robot. So here is a glimpse of our autonomous mobile robot, a pile picker, which is a forklift over AMR. And now Saleh will give the context about the behavior tree.
Hello again. So, what are behavior trees? Why behavior trees? Why do we need them? So, they are a structured approach, a structured way, like when you have a complex set of tasks, a bunch of them, in fact, and you want to have an organized way of, having a task control on it, switching between tasks and all. It's it supports that in an efficient way, and where that efficiency comes from is its inherent nature of being highlighted modular and reactive. So what I mean by modular is like when you have a tree and each part of a tree can be developed simultaneously, maybe tested separately and can be reused, rearranged within your tree or among other trees, and maybe your tree can be a part of some other bigger tree which facilitates higher level task planning. So it was originally from gaming industry where it was used to develop the behaviors for NPCs, and now it's been used widely in industry on AGVs, AMRs, and robotic manipulators like robots and so on. So morning we had an wonderful talk on open science stack where they explained how they leverage the task sequence, AI-driven task sequence generation. So it can also be there in mission layer when it comes to fleet management also. Like maybe you want very high level mission is there and maybe you need a task composition. So it can be giving you that rigid lower layer where the top layers can utilize it in a plug and play way easily. So we are used to state machines, like it was what traditionally we have been doing to model your tasks and kind of switch between them and all. They were very common, simple, and intuitive. Even RAS2 lifecycle has that state machine with states, inactive, finalized, and all. But where comes the problem is when the complexity grows and it becomes cumbersome with too many transitions and states and all those things. Don't get me wrong, like it's still relevant in lower layer and all state machine, but when it comes to complex task switching and controlling behavior tree, that's far better. So it's still scalable and humor understandable framework for our applications, and it's just tree hierarchy. So basically, it's easy to track your flow of tasks. So there is a library PyTree, like for rapid prototyping. Maybe students and researchers will be more interested in it. We have PyTree source for support. Like we can play around with it. It has the XML tree definition kind of thing which was shown in the morning sessions. You would have to develop it with like programmatical way. But if you, it will also benefit your application if your application is on wholly Python and all. So if you think, nah, I'm good with C++, then you can always keep using behavior tree CPP and can do away with this. So what cool features? So what cool features we basically found, like everyone sees at a first glance, so when we want to use behavior tree, is its strong node library, we have a lot many things apart from what is shown here, and we have Blackboard and Groot visualizers. So when coming to node library, let me start with some simple illustrations. Um, so let's say we have a simple tasks, like we have a robot, like maybe you have like our forklift AMR, where you need to do sort of just detect and move under the pallet or something, roll a cage or something, and you need to kind of lift the object. So you need to go in a sequence, detect, move to goal, then you lift the object, hence the sequence. You have to go through all these actions successfully. Then you have like decorator nodes, which are, you can have a different things like retry until successful for max number of attempts and all. When if you feel like if your attempts object direction is gonna fail. Um, so now we have, let me just think. So let's say I fail in the first layer, then maybe want to try out something. Maybe I need to readjust myself and like look at the object from a different point of view. Maybe I introduced another sequence where it's kind of a fallback mechanism. So these modular things can be maybe mixed around, to give you a basic layer, outline on like layer of object and lifting the object, detecting and lifting them. So what blackboards are is like basically they are key value pairs, which is shared between the nodes. From any part of your tree, you can access them and you can use the data. And Groot is a good ID visualizer, like where maybe when you're developing, you can debug these trees, and you can do all sorts of things. It helps with development. So thank you, and over to you, Abhijeet.
So many of you will be using navigation and move it. So navigation 2 from Jazzy onwards is using behavior tree version 4 for navigation task execution. And Nav 2 is incredibly reconfigurable project, mainly because of Steve Masenski and other Nav 2 collaborators, but also because of the use of behavior trees, which makes it easy to rearrange so you can develop your own navigation behavior. Nav2 BT Navigator and Nav2 Behavior Trees are the two packages where you can find the implementation of behavior tree. And Move It Pro SDK is also built around behavior tree CPP. So the two most project which you use are already using behavior tree. That's what makes behavior tree very important. So what motivated our transition to behavior tree? Previously, when we are using ROS1, at that time we were using SMAC for task execution. So it had scalability. It was actually simple, but as the requirement grew complex, then there was scalability issue, and we had to customize a lot for recoveries, retries, and all. It was not maintained properly. There were issues related to crashing when we were using concurrent nodes. So when we transitioned to ROS2, there was no SMAC, and navigation 2 already adopted behavior tree. So we just gave behavior tree a try. And there were initial struggles with behavior tree. There's a learning curve because it's a different framework than state machine. And at that time, 2 years back, limited resources were available. But once we implemented it, we realized its potential, and definitely there is no going back now. So why you should use behavior tree in autonomous mobile robot? So here are some few questions which need to be answered. How you can execute a given task given from the fleet management system to the robot? How you can control robot based on the hardware state? For example, you want to pause a robot when the LiDAR is infringed and you want to resume when it's cleared. How you can combine different tasks like detecting pallet, moving inside the pallet, and then lifting the fork. How to perform recoveries, retries, and small logic like skipping subtask based on some condition. And most importantly, how to perform all this requirement while keeping it simple and scalable. So the answer is behavior tree. It can do it all. So this is the architecture for behavior tree based task execution for AMRs. So on the right hand side, on the FMS fleet management side, there's this robot adapter, which will be giving tasks to robot client, and then the robot client will be calling the execute task action server in the robot behavior tree node, and this robot this execute task extend server will be calling a timer to tick task behavior tree, which will be calling navigation, custom behaviors, and robot vision node based on the task. And there's another behavior tree here that is background BT, that is for the background work and lifecycle management. And we are getting the hardware values from the ROS to control. So we'll be combining some information from the behavior, robot behavior tree and this hardware state, and then we'll be publishing it to the client, which will be giving it to a robot adapter. So this is a closed loop. And this task control service server, which is in green, is for pausing and resuming the robot through robot client. So handling hardware in BT. So in this architecture, there is only one topic, that is hardware state. So it simplifies everything. Like in one topic only, you will be having all the data of the hardware. So based on that, you can, for example, if LiDAR is infringed, you can pause the robot. If it is cleared, you can resume the robot. For example, if the robot is in manual mode, so you need to manage the life cycle of joystick node. You want to make it active so that you can jog the robot. And if it is in auto mode, so it shouldn't be happening like you plug the joystick and robot is jogging in the auto mode. So this will manage the through life cycle. And for example, if you have eco and performance mode, so you want to change the motor parameter based on that to enable power saving or fast speed performance. Then based on the task, you also want to control the LiDAR field, apply or release brake, move the fork up and down. So for that, it's better to use ROS to service and action. So how to pause, resume, and cancel the task? Canceling the task is easy because action is already having cancel feature. So we just wrapped task BT and ROS to action, which make cancellation very easy. So first, once we get the cancel call, we just halt the task behavior tree and then cancel the timer. For pausing and resume, this feature is inherently not there in ROS 2, but through behavior tree we can achieve it. So the sequence which we can follow, we can consider a case where robot is given 5 waypoints to navigate through poses, and robot covered 3 waypoints. And now we call the pause. So in this case, this behavior tree action will cancel the ROS to action and store the remaining feedback. So already the robot has covered 3 waypoints. It will store last 2 waypoints, and then the BT node will be kept on running. But when we get the resume call, then it will send the remaining 2 waypoints to the robot. So in this architecture, there is internal pause and internal pause, which is when the LiDAR or ultrasonic fields are infringed. And then there's external pause, which is called from the fleet management side through robot client. So for that, we implemented task control service. So the server will be on robot behavior tree side, and the client will be on the robot client side. And the blackboard value will be updated for it. Then previously we were using behavior tree version 3, and behavior tree version 4 is having many cool features which simplifies your work. So for example, one is scripting. So scripting simplified implementation. So you can use for example, in this case, previously as I explained, there's external pause and internal pause. You can use just OR operator, and you can store the value in the pause variable, and that too in XML. You don't need to change into CPP. Then if you want to add an offset, you can do just in scripting. Then, for example, if you have multiple hardware and all the hardwares are working correct, then only the main is hardware okay is true. So you can specify like that. And then there are precondition and post-condition, which made, again, the code very small. We don't need to pass the blackboard value inside the BT node. So for example, if there is a node where if the hardware is connected, then you want to set that blackboard value to true. So you can, in that node, you can just specify on success is ABC hardware connected to true. No need to change in CPP, just in XML only you need to change. Other case, like if you have a sequence which you want to skip, if it is target is less than 2, so you can just use success if. It will skip and return success for it. Then there's this while. So, for example, in a case where a robot is moving inside the pallet and the forks, if they are triggered, like it touches the pallet, so in that case, the robot has to stop. So in that case, we can use while just in XML, no need to change anything in the code. That is the reactive behavior of the behavior tree. Then in our case, we are using multiple BTs and subtrees. So to segregate task and background work, we are using task BT and background BT. For background BTs, for running continuously handling background work, and task BTs, whenever the task is given, only at that time it will be called. Also, we have used multiple subtrees. Like for background, there's this hardware initialization. So in the starting, you want to set the LiDAR field. You want to do the homing for the motors. So you can use this subtree. Lifecycle management, as I explained, if it is in auto mode or manual mode, so you want to set lifecycle for navigation and or tele of joy node. So you can use this subtree. Then hardware check, if you have CAN, IMU, LiDAR or depth camera. So you can check whether they are connected or not in the starting only, or when the robot fails at that time also you can check. So you can find out where is the problem. Then sensor topic check. Sometimes it may happen that the hardware is properly connected, but ROS driver might be having issues, so you won't be getting topic. So you can continuously check. So like this, you can have 4 subtrees in background BT. And task BT, depending on different tasks, we can create different subtrees. It simplifies. So for we have done pick, drop, move, park, and charge. So whenever the task is there, depending on that, you can use this switch. It's already there in behavior tree, and you will be calling that subtree. Then whatever things I explained, this is the overall architecture. It may look complex, but it's same what I explained. Then there's another project which is using behavior tree for industrial automation. So traditionally, in industrial automation, PLCs have been used. And now the requirement is like we have to integrate some part of AI for complex image processing. So in that case, customizing the proprietary controllers, it's very difficult. So that's why this project is uses behavior tree and ROS2. So this is by OSRF only. Project name is Nexus, and it's having system orchestrator and work cell orchestrator. And for communication, it's using Xeno. So this system orchestrator and work cell orchestrator, they are both using behavior tree only. So this is the QR code to GPay or PhonePe us. I'm just kidding. This is for our LinkedIn profile. If anyone is interested in the work which we are doing, anyone want to connect or interested in joining, then they can connect to us.
Yeah. Thank you all. Thank you, organizers, open source, open community, and all of you for your attention. Thank you.